Hello, my name is Ein, or you can call me Brian, which is my English name. I am the team leader of Group 8 of the OGO Automotive Design Project. And today I'm very excited to share with you about the progress that we made so far on this challenge. Um, we will start off first with me introducing my team members. I'm the project leader, Brian, the communication manager and top human developer will be responsible by Igor. Mikael will be the driver, speed measurement system developer, and also equipment manager. The rolling resistance test will be responsible by Constantine. Wind tunnel test is responsible by Joshua. Dynamometer test will be responsible by Tim. And finally, I'm also do the driving strategy with Aria. The next thing I want to go through is a small introduction about our project. So recently, TUA has cooperated with EPE Vehicles, which is a small passenger car manufacturer with an open-minded mindset. So they design an electric car, but since the technology is pretty new to them, um, they work with us on and host a project challenge to evaluate the car. So in this challenge, the student groups will be provided a 1 to 5 scale down model of the car for testing. And we use city driving conditions because this is a passenger cars. So the goal for not for only this challenge but for all of the other electric cars is to reduce their energy consumption, which means that they will increase the working range of the car. So in order to do that, we created an approach which has 2 stages. So the first stage will be tank-to-wheel analysis, and we're currently in this stage, which we will identify the variable first, because, for example, we need to know what is the tire friction coefficient. We need to know the power output of the electric motor, etc. And then we will research on existing methods, because before us there are variable people who is also doing the same project or who also wants to improve the driving range of electric cars. And finally, after we have decided what is the best way to improve the car, we will make the test plans. And then at the second stage, when all these has been done, we will do the vehicle implementation. So in this stage, we will choose the most efficient driving strategy based on the numbers that we get from the test case. And then at the same time, we will work on programming the Arduino and the toll payment system. After everything is done, we will do the test drive and we will finalize the product before giving it back to the EPE vehicles. So before we go into the details of the technical parts, I will introduce the order of presentation. So first off, Tim will do the vehicle powertrain, and then Tim will also do the vehicle aerodynamics along with Constantine. Rolling resistance will also be responsible by Constantine. For the driving strategy and Arduino programming, Aria will talk about it before I'll come up with the upcoming plans in the future. So now I'd like to Tim to talk about the powertrain.
I'm Tim and I'm responsible for the dyno test. The dyno test is used to measure the efficiency of the drivetrain by measuring. I forgot.
Oh my god.
It's okay, it's okay, it's okay.
Yes, okay.
I'm Tim and I'm responsible for the dyno test. The dyno test is used to measure the efficiency of the drivetrain by measuring the power consumed by the battery and the power output of the wheels. These values will be obtained by running 3 different tests. The first test with the motor cockwheel removed, the second test with the motor connected to the battery, and the third test with the motor connected to the battery first test, the cogwheel is disconnected from the electronic controller and the roller spins the car wheels in a forward direction. The purpose of this first test with the cogwheel removed is to measure the rolling resistance of the dynamometer, as the goal of the test is to correlate speed, force and efficiency of tank to wheel. The losses between the roller and the wheel should be left out of this equation. In the second test, the electric motor of the car is connected to the battery via the motor controller. The wheel speed is kept constant. At that speed, the output power can be measured. In the third test, the electric motor of the car is connected to the battery, but the motor and the roll bench are stationary. At that moment, the power can be measured. In order to drive the electric controller, power supplies are required. The purpose of this test is to measure the actual losses. Results of the dyno test. The following parameters are being measured during the dyno test. With all the measured data, the total power loss can be calculated and the efficiency of the powertrain can also be calculated. The obtained results contribute to the tank-to-wheel analysis and they will give an efficiency map of the model car, depending on both speed and force. The efficiency map will help the driver to drive the car as efficiently as possible. Aerodynamic drag test. The aim of the aerodynamic drag test is to calculate power losses of the model car due to aerodynamic drag. As a lot of power losses in electric vehicles come from the aerodynamic drag. The aerodynamic drag force is obtained by the following formula, and in this experiment this CD parameter will be measured with different rear rings of floor and wheel covers. The frontal area of the car is measured with a frontal area photo run through Digimizer image analysis software. And Constantine will explain the actual aerodynamic drag test in the wind tunnel.
I'm Konstantin. I will be explaining the rest of the aerodynamic drag test and the rolling resistance test. The aerodynamic drag test basically consists of is done in a special building. This one will be done in TUI's very own wind tunnel in Ventur. Basically, what happens is air is pushed to the front of the car, which exerts a force on the car itself, and according to Newton's third law, the car pushes with an equal and opposite force, and this force sensor then gathers the data for that force and stores it in a drive. The aim of this experiment is to find the optimal car architecture that will produce the least amount of drag. Therefore, the car will undergo a series of tests with three different setups. The first setup will be with the original rear ring that was given to us from the faculty staff, the wheel covers, and the group designed car floor. The second test will be performed with a replaced rear ring that the group will design, and the third test will be with no rear ring. For the aerodynamic drag test, this group designed two components. At the beginning, nobody in the group really had experience with electronic sketching, so for the past 2 weeks, that was our focus. We focused on getting the basics of AutoCAD, and this is what we came up with for the car floor. The car floor basically is used to smooth the car's airflow, and therefore it reduces the drag coefficient. Same thing with the rear ring. The aerodynamic drag test, the aerodynamic drag force, along with the rolling resistance force, make up around 80% of the power losses in electric vehicles. So getting a low air drag force is important to maintain or to increase the tank-to-wheel efficiency and get the most range out of the battery of the car. Next up is the rolling resistance test. So the test is used to measure the rolling resistance force which is a force that opposes the motion of a body, a rolling body. As we can see in this diagram, a force is applied to the body in this direction, and the rolling resistance opposes this force in the opposite direction, and it is on the wheels or the rolling component. The force is equal to the rolling resistance coefficient times the mass of the vehicle times the gravitational constant times the cosine of the angle of the incline of the surface. But since all the tests will be done on a flat surface, this angle can be neglected. Therefore, the power losses will then be equal to the rolling resistance coefficient times the mass of the vehicle times the gravitational constant times the velocity of the vehicle. The two constants in this equation are the mass of the vehicle, which is 11.95 kilograms, and the gravitational constant, which is 9.8 meters per second squared. The variables are the longitude of velocity, Vx, which will be measured by a special Arduino Duo module, which measures the speed of the rotor and converts that to the speed of the wheels. From all these variables, when all these variables are obtained, the rolling resistance coefficient can be calculated. In order to measure the rolling resistance, there can be multiple tests can be done, but the group decided that the most appropriate test for this project is the close-down test. Essentially, what that means is a car is pushed from a certain velocity and completely let go, so that the forces resisting its motion can stop it. And along the way, the trend of decreasing velocity is measured over time, and with this we could calculate the deceleration of the car due to those forces. The test will be done in two different settings, with the electromotor connected to the car and with the electromotor disconnected from the car. And this way we can find the rolling resistance both of the internal components and of the external components of the car. The value that we will get for the force should be Fst, which is basically equal to the resisting forces, or the rolling resistance, and the drag force. Other forces also act on this, contribute to this force, but they're small and insignificant and will not be accounted for in this test. From this equation, we can get the equation for the rolling resistance coefficient, this one, where Ax is the deceleration of the car and Fd is the air drag force, which will be obtained through the wind tunnel test. One thing to note is that, as we can see in this graph, the coefficient of rolling resistance is dependent on the velocity of the vehicle, and the aim at this point is to find the exact function over the speed. However, we are not sure if we will be able to do so. So, if it is not possible, we will keep the rolling resistance coefficient a constant. Similar to the other tests, the rolling resistance test will be used to increase the tank-to-wheel efficiency, of course, and the battery range, but also the rolling resistance coefficient will be used to calculate the optimal driving strategy, again, in order to increase the efficiency of the vehicle.
Hi, so I will be discussing the software and the strategy, and that includes the one main component that we have to monitor the speed. So for the speed, what we want to do is we're going to be using a lot of code, and we have a bunch of different devices built onto the car. So first we have the Arduino model that we already discussed. This is a central hub for all of the processes. So we wrote our code. One of the guys that was responsible for writing the code, he took a replica of this module home and he wrote the code, and we tested it, and then we did some simulations to see if it was working. We then brought the module back to the where we're working, and we tested it out. It worked really well because it was giving us an output and it was what we were expecting. However, the scale was a little bit off, and that led to us having to make modifications to the program. So the way this works is that here we have a few different components. We have a cogwheel and this main thing, which is a speedometer. For this we have 4 different magnets that are all going to spin, and it's going to be detecting the distances. So if there's a higher distance, that means that there is a lower voltage output, and with a lower distance we have a higher voltage output. This we can use to put it again into a few different formulas and equations, and with that we can determine the RPM and how fast the car is actually going instantaneously. And then another nice feature that we have is that we have 3 different LED bars built into the car. We have 2 on the sides and 1 on the front. These bars, all 3 of them are individually equipped with 16 5th-bit registers, which means that every single one of the lights on these bars can be programmed individually to perform and show whatever we would like for it to show. We decided that it would be the most optimal and efficient way to use these to alert the driver of different conditions that we want the driver to meet. For example, we want to have the car produce a specific optimal power output, so that we can sort of detect that and make sure that the driver is driving at the speed that we want him to. So we can have the LED bars either flash or turn on green or red to show how much, if the driver should speed up or slow down, so that the output is what we are expecting and what we want. So we decided that the LED bars, their main purpose is going to be to alert the driver. So then for the driving strategy, we decided that since this is a city car, we have to make sure that the conditions it meets also satisfy the city car driving situations. So for example, we don't want the car to accelerate or brake too hard, because that's not the way that it's done in cities. There will be constant acceleration, constant deceleration. There will also be braking, but the issue with braking and accelerating is that it uses a lot of power. If we brake, the car stops, and then we gotta put in a lot of power again to start the car. So it would be the optimal way for us to limit the amount of braking and accelerating. And then we also, through the rolling resistance test, we aim to find like an optimal driving radius. If we determine that, we can determine how much output we'd have at which corner, and then we could find an optimal turning radius. And for the rest of the driving strategy, as far as we got, we have to just get the results from the test plans that we have created. We need just so that we can piece everything back together and we can do the calculations, and yeah.
Don't die like this, bro, don't! Anyway, I want to tell you about the upcoming plans. So, after we finish the stage 1, which is the tank-to-wheel analysis, we will do the vehicle implementation. So first, we will try to finish up the Arduino programming as soon as possible, because it is the hardest part of the whole process. And then the user interface, which is how the driver will communicate with the LED bars. So for example, like the guy who I just pushed has said, when the LED bars have like a green color, it means that we are reaching the efficient speed, and etc. There are many other ways. And after everything has been done, and we think that the product has reached enough quality, we will finalize the driving strategy before giving it a test.